So, good morning. So, we will look at the different models that can be used to predict thermal conductivity, effective thermal conductivity of nanofluids as a function of the nanoparticle volume fraction, and most importantly also the dependence on temperature. So, the dependence on volume fraction can be accounted by models such as the Maxwell's model. So, depending on the value of phi, whether it is 0 or 1, it takes the case of for example, phi equal to 0, it takes the case of base fluid, phi equal to 1 the nanoparticle, and some kind of weighted value of k in between Kp and Kf. There are also other models which account for the shape of the particle, because the Maxwell's model is actually for a spherical particle. So, a modification to that is called the Hamilton Crosser model. So, this is quite popular when you want to apply this to non-spherical particles. So, we have a parameter called the shape factor. This parameter is denoted by the notation n, and this is equal to 3 by psi. So, where psi is nothing but it is called the sphericity of the particle. So, it denotes how spherical the particle shape is. So, if sphericity is equal to 1, this is a perfectly spherical particle. Okay. So, if you substitute therefore n equal to 3, so into this expression you will get the same expression as the Maxwell's model. Okay. So, therefore, for the limiting case of a spherical particle, the Hamilton Crosser model collapses into the Maxwell's model, and for values of psi which is dot equal to 1, you can look at particles of different shapes. Okay. But nevertheless, and there is also something called as the Davis model, which also includes some of the higher order terms, may be important if you want to look at the interaction between the nanoparticles, and if you do not include the second order and third order terms, then it becomes again equal to the Maxwell's model. So, you see that these are the fundamental models used widely to predict the effective thermal conductivity of the nanofluid as a function of the volume fraction. But very important behavior is the variation with temperature. So, which none of these models can account for. Okay. So, the variation in temperature is very clear. You can see that although the base fluid shows a reduction in thermal conductivity with temperature, however, the nanofluid on the other hand shows a continuous increase. So, this can be predicted, or this can be modeled only if you account for the Brownian motion. The Brownian motion is the most important mechanism which can say why the thermal conductivity should increase with temperature, right. So, none of these models are actually accounting any temperature dependence into them. So, therefore, so one of the more recent models is our own work in our lab here. So, this is published in 2013 with our PhD student in our lab. So, this model is a more comprehensive model which we have built that accounts for two components. So, one is the random motion due to the Brownian effects. So, that is called the sheet dynamics. Okay. So, the sheet dynamics part consists of three components. So, one is the thermal conductivity of the base. So, the overall conductivity of a nanofluid. Okay. So, now if you break this into two components, one is the sheet dynamics component, the other is a percolation component. The sheet dynamics component includes the thermal conductivity of the base fluid, okay, to which we add the nanoparticle. So, therefore, we also account for the thermal conductivity only due to nanoparticles. So, that expression is given separately. This is coming from what we call as effective medium theory. So, if you put here phi equal to 0, this part will be 0, okay, and phi tending to 1. Okay. So, phi can never be directly equal to 1, but phi tending to 1, the dm the ratio of dm by Lg will be approaching 1 for that case, okay, because dm is nothing but the molecular diameter of the base fluid, which is of the order of close to angstrom, right. Whereas, if you are talking about Lg, Lg is the phase size of the nano sheets. That means, if you look at this construction of a unit cell. So, we are looking at 1 unit cube of the entire nano fluid, in which we have these nanoparticles dispersed. So, the nanoparticles can be generic, they can be of any shape, any cross section. So, if you look at a generic case, they can be like sheets which are linked to each other, these are forming certain links. If you have pure particles, then you may not find this linkage structure to be dominant, it will be just dispersed. But if you look at nano sheets, for example, carbon nanotubes, so these more likely form chains. Okay. So, these chains consist of lot of these micro sheets which are held together as linkages, and there are several parallel layers like this. Okay. If you therefore take the length of any particular micro sheet, so that length is basically the phase size of these sheets. Okay. So, once you put this, so therefore, the value of Lg will be of the order of few hundred nanometers, whereas the value of dm will be few angstrom. So, therefore, if your phi is going towards 1, something like 0.99, so this 1 minus phi will be a very small term. So, therefore, that multiplied by Lg will go to the value of dm. So, that the denominator and numerator the dm by 1 minus phi Lg will be approaching unity, and therefore, the value of k EMT will approach the value of Kp, okay, for limiting case of phi approaching 1. So, you have therefore contribution from the base fluid, you have contribution from the nanoparticles, plus you have contribution from the Brownian motion. So, these are the 3 components which are included in the sheet dynamics part. Okay. So, the contribution from the Brownian dynamics is simply given by an expression which is a function of the Brownian velocity ub. Okay. It is also a function of other things like volumetric heat capacity, nanoparticle volume fraction, phi, and d by temperature, and so on, and also the mean free path. Okay. But most important is it is a strong function of the Brownian velocity. So, the Brownian velocity is given by the Einstein expression. Okay, this is also called the Einstein-Stokes expression. This tells you that the Brownian velocity is directly proportional to the temperature, okay, and inversely proportional to the size of the particle. The smaller the size, your larger is your random velocity, and so is the dependence with temperature. Okay. So, therefore, if you are applying this particular expression, so this now accounts for dependence of thermal conductivity both on volume fraction as well as temperature through the Brownian motion. So, therefore, if you are able to use this model, you can accurately predict the variation of thermal conductivity with temperature. So, we have checked this model with different kinds of nanofluids, including particle type nanofluids, including sheet type of nanofluids, and they seem to work very well and good prediction. So, now the other component which is very important for the sheet type of nanofluids like carbon nanotubes, okay, this is called the percolation part. So, as I said, if you have carbon nanotubes, so they will form linkages with several of these nano sheets which are linked together in a chain, and several of these chains in parallel. So, therefore, we have to also look at the conduction through these chains. So, there is a conduction of heat from, for example, left to right. So, there will be a conduction of heat through these chains because they form a conduction network, okay, similarly through them. So, not only it is a random motion, but also they form a chain which will promote a network for transport of heat. So, this is called the percolation component, and to understand this percolation component, we have to first estimate how many number of such parallel chains can be formed. Okay. So, there is one empirical expression we have used, to calculate this capital M, which denotes the number of parallel chains, and within each chain you have several nano sheets. So, you can say capital N here represents the number of nano sheets in one chain. Okay. So, that is basically given by this N here. Okay. So, once you know the number of nano sheets in one chain, you can use this empirical correlation to find out how many number of chains that can be actually formed. So, now you can draw a resistance network analogy for the thermal resistance. Okay. That means, what are all the resistances acting? So, you have, if you are talking about heat conduction through this is all in series, right. So, through one chain this is in series. So, through the nano sheets you have conduction, and between the two nano sheets you have interfacial thermal resistance. Okay. So, actually these two nano sheets are not exactly touching each other, there is a small gap I mean you have actually the fluid separating these two. So, there is actually a contact resistance between the fluid and the solid. So, therefore, in effect if you take one nano sheet, you have conduction resistance plus twice the contact resistance on either ends. Okay. So, that is the series component of the resistance. You also have a parallel component of resistance, which is heat conduction through the base fluid itself, right, and therefore, these M links are all in parallel. Okay. So, therefore, if you draw the resistance network analogy, so essentially you have in series the contact resistance on either ends and you have the conduction resistance through the nanoparticle. So, these are all in series, and you can have this for n number of chains. So, this is for one nanoflake or nanoparticle. Okay. So, since you have capital N number of nanoparticles in one chain, so they can all be in series, and in parallel you have for m number of chains, nanoparticle chains. So, you can have all these in parallel. So, you have m parallel chains and n serial nanoparticles forming a particular chain. Okay. And not only that, you also have the fluid resistance which is acting in parallel. Okay. So, for each unit cell, okay, if you assume this is one unit that is one nanoparticle. Okay. So, you also have the base fluid which is conducting the heat parallel. So, therefore, for one nano sheet you have the base fluid in parallel, and you will have such m parallel linkages acting. So, and then you have to repeat this for capital N number of nano sheets acting in one link, right. So, you have simultaneous resistances in series and parallel. So, therefore, the net effective resistance, okay, you can actually very quickly you can derive this. So, because first consider only the series the parallel resistances here. Maybe you can all try this out now. So, you consider only this resistance of one nano sheet all in parallel. So, find out what is the effective resistance of this. So, that is 1 by R effective parallel is equal to 1 by. So, you have in series RC 2 times RC plus RIP, and there are m such linkage m such linkages in parallel. So, therefore, this should be plus 1 by 2 times RC plus RP. So, m number of times. So, therefore, you can replace this by m by this, right. Now, plus you have the base fluid which is acting in parallel for a particular nanoparticle. So, therefore, your R effective parallel will be nothing but RIP plus 2 times RIC times RFIP by this is m divided by plus. Okay. So, if you if you take the reciprocal of this. So, this is basically product in the denominator, summation in the numerator. If you take reciprocal, product moves to the numerator, reciprocal, the summation moves to the denominator. So, and then finally what do you have? So, this is one set of effective resistance. Now, you have series of them. So, capital N number of them. So, therefore, the effective resistance should be summation of this over n number of these nanoparticles. Okay. So, therefore, finally, from that you get this expression. So, all of you can quickly check if you are able to get this. So, basically we start with one nano sheet, everything in parallel, okay, and then for extending this for n number of nano sheets in over all the linkages. Okay. So, basically this RAP is nothing but the conduction resistance through each nanoparticle, and RC is the contact resistance between successive nanoparticles.
So, that chain there is fluid resistance in the top layer.
Yeah.
So, there will be same resistance in the down layer or not?
We are considering together as one fluid resistance.
Means, upper resistance as well as lower resistance is a single.
Correct. So, what we say is the total fluid resistance is included as one resistance in parallel, okay, and each of these links we are considering the resistances separately in parallel. Okay. So, this is a this is the approach we follow. Therefore, from once you estimate the net resistance, so we can calculate the thermal conductivity component due to the percolation. Okay. So, how do you calculate? So, using this expression finally L by R net ASL. So, you remember your Fourier's equation where we express your resistance, conduction resistance as L by Ka. So, from which we can calculate K as L by Ra. Okay. So, same way now our L is nothing but the length of the cell, that means this cell is a unit cell with a particular length L, and this has a total net resistance R net and the corresponding cross sectional area of this cell ASL. Understand? So, from this we get the K percolation component, and we can also estimate the conduction resistance from another empirical correlation, which depends on the thermal conductance per unit area, and depending on the type of nanofluid you have to use the value of G appropriately. So, from the components of K percolation and sheet dynamics, we use a power law rule to calculate the total thermal conductivity of the nanofluid. So, we use a factor alpha and 1 minus alpha to take the individual contribution. Suppose if there was, it was purely spherical particles, then what will happen to the percolation component? Percolation component should not be there. So, if your value of alpha equal to 1, then K nanofluid will be only K sheet dynamics. So, that means only Brownian motion is responsible for the increase in thermal conductivity. But if you take a nanofluid which is purely carbon nanotubes, then these carbon nanotubes form these flake structures, linkages, okay, and your Brownian component will be almost 0, because they cannot move as fast like the spherical particles. So, in that case your alpha will be 0. So, your total effective conductivity will be only coming from the percolation conductivity. So, for nanofluid like graphene, this has somewhat intermediate, it is neither too big to form huge linkages nor too small to just simply move around. So, it will have contribution from both components, Brownian component as well as the conduction component. So, in that case we use a value of alpha maybe 0.7 or 0.8, okay, and it will take into account both these components. Okay. So, therefore, the alpha is called the sheet distribution factor. So, it tells you how much weightage you have to use for the percolation component versus the the Brownian motion. See, for example, graphene we use the value of 0.34. Okay. So, we give more weightage to percolation for the graphene compared to sheet dynamics. Okay. For purely a spherical nanoparticle like alumina, copper, metallic nanoparticles, so then we put alpha equal to 1. So, pure sheet dynamics component. So, this is a very comprehensive model. So, which accounts for explanation on why and how the thermal conductivity increases with temperature, with volume fraction, not only for one type of nanoparticle, but different shapes of nanoparticles. Okay. So, this is probably one of the best models that are available so far in literature, which can be used for wide different kinds of nanofluids, and you can get satisfactory agreement. Okay. So, this is one component. The other is to estimate the viscosity of these nanofluids. So, now when you add the nanoparticles to base fluid, your viscosity also will increase, okay, and therefore, you do not know two things. One, what is the effective viscosity? You cannot take a simple volume average for effective viscosity here. You have to determine them, or you have to have a good model which can predict, and you do not even know whether you will always get a Newtonian fluid. Okay. So, that is the second question. So, therefore, if you want to simply estimate only the viscosity, you can use a viscometer, okay, which gives you directly what is the dynamic viscosity of this fluid. But if you want to really know if this is a Newtonian fluid or not, we cannot use a viscometer, but we have to use a rheometer. Okay. So, rheometer, it gives you what is the, for a given shear stress, it gives you what is the corresponding strain rate. So, you plot stress versus strain rate versus stress, and you will yourself know whether this is a linear curve or it is changing somewhere, so that we can approximate this as a Newtonian fluid or a non-Newtonian fluid, right. So, therefore, the rheometer in that sense is even better to assess the fundamental Newtonian behavior of these nanofluids. But most of the basic nanofluids like alumina, copper, water, even carbon nanotubes or graphene at very small volume fractions, mostly they behave like a Newtonian fluid. Okay. So, we can use these like the way we measure thermal conductivity with a hot wire technique. We can measure viscosity of any fluid need not be nanofluids, so either using a viscometer or a rheometer, and we can get the effective viscosity, and we can see that this is a very strong function of once again the volume fraction. Okay. The volume fraction increases considerably, and also with the temperature the volume fraction drops. Okay. So, for the fluids again with increasing temperature the viscosity actually drops. Okay. So, overall the nanofluid also shows this behavior. However, you have to have again accurate models which can predict the behavior of variation of the nanofluid viscosity with respect to both nanoparticle volume fraction and temperature. Okay. So, the models such as the Einstein model, Batchelor model and Chandrasekhar model. So, they are used for suspensions, they have been used for a long time, but they are all only functions of phi, and they have not comprehensively built in a temperature relationship. So, the temperature relationship effectively comes from only the base fluid viscosity as a function of temperature. Okay. So, the model by Abunada for example has explicitly dependence on temperature for the nanofluid also. So, these are some of the common models which can be used. Some of them have mostly they have been obtained from experiments and some from simple theory. Okay. So, we have also proposed a similar model using our percolation component and the sheet dynamics component. So, it is not that the percolation and sheet dynamics affects only the thermal conductivity, but also they play a very important role in the viscosity as well. So, your sheet dynamics component and percolation components for viscosity are separately calculated using these expressions. For example, here L star is nothing but the non-dimensional length, which is the size of the nano sheet divided by some critical length. Okay. And D is called the percolation network dynamicity factor, phi is the volume fraction, alpha is the sheet distribution. So, if suppose you take the case of pure spherical particles, percolation component should be 0. So, in that case you just only have the sheet dynamics component. So, if you substitute for example alpha equal to 0, so you have only the sheet dynamics component and the percolation component will disappear. Okay. So, you have mu percolation will be only mu base fluid. So, mu base fluid plus the sheet dynamics component will be there. Okay. So, mu naught here from the dynamic sheet dynamics point of view, it is again a function of the Brownian velocity. So, what it says is the Brownian velocity also affects the viscosity, not only the thermal conductivity, but also it describes the viscosity increase. Okay. So, higher the Brownian motion, more is the increase in the viscosity, and so this is and again the dependence on temperature is also brought in through the Brownian velocity. Okay. So, we have used this model. For example, if you take the case of carbon nanotube, the value of this non-dimensional length L star is approximately equal to about 10, and if you use this, we have found that this model can also very accurately predict the effective viscosity of the graphene water nanofluids, carbon nanotube water nanofluids. So, one on the left is the graphene water, the other on the right is carbon nanotube water, all functions of different volume fractions and at different temperatures also. So, not only the volume fraction dependence, but the temperature dependence is also properly predicted by these models. Okay. So, we will finally move now into the heat transfer characteristics. So, we have whatever we have talked about till now, it is only the case where it is static fluid, where we measure the thermophysical properties. Now, when you start motion, bulk motion, what happens if you have nanofluids replacing the bulk fluids? So, for that several experiments had been conducted on the forced convection, single phase forced convection, natural convection, then phase change. So, quickly I will run over all of these. So, the forced convection experiment also we have had in our lab before students who are doing this. So, this is a kind of a setup where we heat the tube using a DC power supply and we pass fluid, first the base fluid, and look at the Nusselt number, calculate the Nusselt number of the base fluid by measuring the heat flux and also the temperature distribution along the wall of the tube. Then we replace this with the nano fluid and again redo the same thing, and then we plot the ratio of the Nusselt number of the nano fluid by Nusselt number of the base fluid. So, and we check what kind of enhancement we get using nano fluid. That means, it is not just enhancement coming from thermal conductivity itself, but that coming from the convection component, okay. Because if you define Nusselt number, the so if you say H is nothing but heat flux divided by T wall minus T m, this is your bulk temperature or bulk mean temperature. So, your Nusselt number now becomes H x by K, and this Q at the wall is nothing but minus K dt by dy, say at y equal to 0. So, now for the nano fluid this becomes K nano fluid. So, if you use nano fluid in the definition of Nusselt number, what happens? If you substitute this, this will become minus dt by dy y equal to 0 x by T wall minus T m. So, the thermal conductivity gets cancelled out. So, that means, any increase in the Nusselt number, if you replace the base fluid with the nano fluid, should be purely because of increase in the temperature gradient and not because of increase in the thermal conductivity, okay. Whereas, if you look at H and if you look at values of H can be higher, but Nusselt number, if you divide it by thermal conductivity of the nano fluid, the effect of thermal conductivity increase will be compensated. So, that gets cancelled out. So, essentially you are only relating Nusselt number to the temperature gradient. So, if your temperature gradient increases, that means you are saying the nano fluids have a better heat transfer characteristics. So, most of the literature, what they do is they mainly plot heat transfer coefficient, but of course, when they are doing this, so they sometimes have this problem where for the base fluid you use K of base fluid, and for the nano fluid you use K of nano fluid. So, you do not know whether the increase in H is due to the higher value of thermal conductivity or it is actually due to increase in the temperature gradient, okay. So, this is actually where some of the literature becomes confusing, and the correct way of plotting it will be to actually plot the Nusselt numbers, okay. So, the Nusselt number does not have the enhancement due to thermal conductivity. So, there are some standard correlations for laminar flows. So, one is proposed by Zhuan and Li, so which states that even in these are average Nusselt numbers. That means, you are not looking at either developing region or fully developed region, but overall for the entire tube which has both these components, developing and developed, you are calculating the average Nusselt number, and this average Nusselt number is expressed as a function of Reynolds number, Prandtl number, now also as a function of the nanoparticle volume fraction. And for example, Zhuan and Li have used Peclet number. Peclet number is nothing but product of Reynolds and Prandtl number, and but however this is defined for the nanoparticle. So, that means we use the diameter of the nanoparticle in defining the Peclet number, okay. So, these are correlations built from lot of experiments. So, experiments like these for heat transfer coefficient, Nusselt number have been done for different Reynolds numbers, Prandtl numbers, different volume fractions, and they have built a very detailed correlation, okay. And similarly, there is one by Maiga et al. In 2005. So, depending on the boundary condition, whether it is a constant wall temperature or a constant wall heat flux, they have given two different expressions as a function of Reynolds and Prandtl number. So, overall what it says that if you replace your base fluid with nano fluid here. So, if for example, if you put epsilon p is the volume fraction, if you put this to 0, you get the base fluid average Nusselt number, and if you add nanoparticles to this, the Nusselt number is increasing. Okay. So, therefore, most of the experiments say that the addition of nanoparticles lead to an improvement in the convective heat transfer rate. Okay. So, this is a Nusselt number. So, you can say that this is not due to thermal conductivity increase alone, but also convective heat transfer enhancement. Okay. The thermal conductivity enhancement will already contribute to conduction heat transfer, but we are only looking at temperature gradient, which is the measure of convective heat transfer increase. So, clearly most of the experimental studies agree that there is a increase in the Nusselt number with the addition of nanoparticles, but only the percentage increase is not very consistent. So, some people claim it can be 10%, some people claim it can be 15% or some 20-25%. So, there is not a very consistent number. So, similarly in turbulent flows also they have seen that there is a possible enhancement with addition of nanoparticles. So, same Juan and Lee themselves have conducted experiments in the turbulent regime, and they have again given a similar expression similar to the laminar flow regime. So, for the turbulent flows also, okay, as a function of the nanoparticle volume fraction and Peclet number. So, only the constants are little different. Okay. So, some people have also used the Dietz-Boelter equation, which says that there is a dependency on Reynolds number to the power 0.8 and Prandtl number to the power either 0.3 or 0.4. They have modified that a little bit for the nanofluids, okay, by changing the constants for the Prandtl number and also the constant in front, that is 0.021, and this was given by Park and Cho. This is a very simple expression, does not account for the volume fraction, right. So, whereas the expression by Juan and Lee explicitly states that for different volume fractions you have different values of Nusselt number. So, these are average Nusselt numbers. Now, coming to natural convection on the other hand, so the experiments done by Putra et al. So, natural convection in a cavity, okay, show that however, unlike the forced convection experiments, there is a deterioration in Nusselt number in the natural convection case, because the problem here is if you add particles with a density higher than the base fluid. So, your effective density is increasing, and therefore, what happens to the buoyancy force? It reduces. Okay. So, the higher the effective density, the smaller is the buoyancy force, and therefore, the natural convection which is a strong function of density. So, a lighter fluid will be able to experience natural convection better than heavier fluid. So, therefore, there is a deterioration with the addition of nanofluids in terms of natural convection. So, nanofluids are always not giving better heat transfer everywhere. So, depends on whether you are in the forced convection or natural convection. Okay, but however, when we did these experiments in our group, we found that yes, there is a deterioration we find as long as you use the regular spherical nanoparticles like alumina, but if you move towards carbon nanotube, flake type of nanoparticles, on the other hand we see an enhancement. Okay. So, in this particular figure, the first figure, we have 0.1% volume fraction of all nanofluids. So, we have plotted the Nusselt number of the nanofluid by Nusselt number of the base fluid. Okay. Therefore, this value equal to 1 means it is equal to the base fluid value. So, if you look at carbon alumina, so alumina shows that for all Rayleigh numbers, that is always less than the base fluid, or at the best it is only equal to the base fluid, whereas when we add carbon nanotube and graphene, they show enhancement of up to 35% or 30% at Rayleigh number of 10 power 6. So, if any nanoparticle addition which contributes to overall increase in the density should result in a deterioration of buoyancy. So, why does carbon nanotube and graphene contribute to an enhancement? So, this was again something which we cannot explain very simplistic ways. So, then we found out that there are slip mechanisms which play a very important role. We did a scaling analysis in which we found out that several forces like drag force also play a very important role apart from Brownian force and so on. So, what we have obtained from the scaling analysis is that drag force is a very important contribution, especially if you look at flake type of nanoparticles like carbon nanotube and graphene compared to spherical nanoparticles. So, that is causing an enhancement even though the overall density is increasing. Okay. So, the heat transfer or the natural convection is augmented by means of this drag force. Okay. So, that is the only way that we can explain why certain nanoparticles like carbon nanotube and graphene can result in an enhancement, while the general theory is any heavier nanoparticle should contribute to a deterioration. Okay. So, these are some recent results which we are in the process of publishing. So, these are with respect to the single phase convection. Now, when we go to phase change, for example, pool boiling, that is we just have a cavity filled with nanofluid and we look at the boiling characteristics, we are finding that generally with increasing volume fraction the heat transfer coefficient decreases with the nanofluid. Okay. So, if you therefore plot Q versus T wall minus Ts, you take the ratio of at any value of T wall minus Ts you calculate Q, the value of Q will be smaller if you add nanoparticles. So, that means the pool boiling heat transfer coefficient actually comes down with the addition of nanofluids. Okay. So, therefore, if you plot this as a Nusselt number, you can see that the Nusselt number actually deteriorates with the pool boiling case. Okay. Now, we have also some correlations developed from our lab itself. So, Professor Das and their group, they have done this for different concentrations and for different heater configurations. So, depending on whether you have a smooth heater or rough heater, a rough heater will have a higher value of Nusselt number compared to a smooth heater. So, you can see all these constants are multiplying constants are larger in the case of rough heater because of the overall higher heat transfer coefficient, because the roughness will promote additional nucleation sites which will improve the nucleate boiling capability, right. So, these are some simple correlations in which there are functions of Reynolds number. Here Reynolds number you have to be careful, it is not the flow Reynolds number, it is based on the velocity of the nucleating bubbles and the bubble diameter. Okay. So, these bubbles which are just rising from the surface of the heater all the way to the top. So, they have a certain bubble velocity and bubble diameter, some average values which you can put in, and using that you can predict the Nusselt numbers. So, these are for the pool boiling case, and a very important aspect of nanofluids is not only the deterioration of heat transfer coefficient, but the critical heat flux is enhanced by the addition of nanoparticles. This is very important, for example, in nuclear safety. Okay. So, if you are talking about boiling water reactors, so these boiling water reactors they are boiling at say certain values of critical heat flux. Okay. Now, if you increase the value of critical heat flux, the chance of transition from nucleate boiling to film boiling is reduced, because you are augmenting that gap. Okay. If this was lower, very quickly you can transition from the nucleate to the film boiling. So, this is very good, this will prevent from the dry out, I know that can lead to vapor pressure increase and explosion chances and all that. So, from a cooling point of view, this is a very important aspect of nanofluids. So, in the case of pool boiling, you see that the critical heat flux is augmented and very large values, sometimes it is of the order of 200%, sometimes it is of the order of 100%. So, finally, coming to flow boiling, there have not been many studies. So, flow boiling of nanofluids. So, there also in the flow boiling also they have shown that the critical heat flux can be augmented by the use of nanofluids. So, and this is so for different Reynolds numbers. So, as you change the Reynolds numbers, the critical heat flux in flow boiling increases, and also with the addition of nanoparticles there is an augmentation in the value of critical heat flux. So, I will kind of stop here. I think with this kind of gives you a overall summary about the heat transfer convective heat transfer characteristics, because there are still lot of topics which are for ongoing research is being conducted. So, this is not a closed ended subject. So, I am only giving you some important correlations which you can use, but the other things are still being developed. So, with this we will stop our discussion on nanofluid, and from tomorrow the next couple of classes we will look at our last topic, which is measurement techniques in nano and micro scale. So, I will see how much I can basically cover in these 2 classes. I will try to brush through them. Okay.